Okay, hello everybody. Today we will talk about parsing, especially the context-free grammar parsing. I will give you two techniques for parsing. One of them is going to be a bottom-up parsing. The second one will be top-down parsing. And if we have time, we will start talking about the parsing of the dependency grammars. Remember, last time we talked about two types of grammars. One of them is the context-free grammars. Context-free grammars context-free grammars are a grammar type within the Chomsky hierarchy, and they say that if you have rules, the rules has to be like this, where on the left side you have a single non-terminal, and on the right side it could be any combinations of terminals and non-terminals. And if you specify your language like this, it becomes a context-free grammar. Why do we call this context-free? Because everything about this rule depends on this non-terminal. We don't talk about any context. Okay. The other type of grammar was dependency grammar. Dependency grammar was, it is not as strict as these context-free grammars, and in dependency grammars, word order is not important. The important thing is the dependencies between the words. We specify the dependencies between words that can happen in any position on a sentence. So the word order is not important for dependencies, which is a good thing for many languages like Turkish, because Turkish is kind of word order free language. We shouldn't say word order free, but it is not as strict as English or similar languages. So as I said before, we will start talking about the context-free grammars, then talk about the dependency grammar parsing next. So last time, I think, yes, last week, people asked me about the midterm exam. When should we do it? Next week, Monday, is your midterm date. Okay. During the class time, we are gonna do an online midterm exam because at the beginning of the semester, remember we said that for the graduate students, the midterm could be a face-to-face, real in-person midterm, but after that things has changed. Anybody coming to university is not wanted anymore. So next week on Monday during the lecture time, starting at 1:30 p.m., we will do our midterm. I will send you the midterm. I will send you the midterm instructions on the weekend, and you will read them carefully and you will follow them. So for the midterm, you need to have a key, of course, a computer with a camera and a microphone. Okay, during the exam, you will have your live connection, and somebody will be proctoring you remotely, and we will be recording all the people in the class. Okay, so midterm exam is on next week. It is going to be, I think, December 7th, 2020 at okay. So let's go back and continue our discussion about parsing. Okay, as we said
Sure,
before.
can I ask you something before we start?
Sure.
I have another exam at the same date, like 2 hours later from this lecture at 3:30.
How come you can take two classes that overlap?
Only 1 hour of them overlaps. The system allows it.
Okay, I don't think that our exam will be longer than 2 hours. You will have 120 minutes.
Okay, thanks.
And in case if I give extra minutes, just ask the other instructor saying that you have an exam. It might be a little bit longer. Okay, and ask him if you can have maybe 10-15 minutes more if I extend the exam. I don't think that that's going to happen, but okay.
Okay, thanks.
What class is that?
151, Mehmet Hoca's course.
151? You are taking 151?
Yeah.
Why you don't?
I didn't take a sports lecture, and they removed the sports lecture this semester, so they gave me that instead.
Okay. So that's not a highly technical class. So okay. So parsing with context-free grammars. As I said before, we will look at two types of grammars. Okay. Whatever look at, we never leave this out. Ambiguity will be always there. Okay. So we will talk about ambiguity. Two types of when we look at the both bottom-up, top-down parsing techniques, ambiguity will be there. Also, there will be lots of other problems, but ambiguity is our most serious problem. CKY parsing is one bottom-up parsing type. We will look at it, and then later we are going to look at the top-down parsing. None of these parsing methods will handle ambiguity. Okay, ambiguity will stay there, but the important thing is that these parsers, both of them, they will say that you could parse this tree either this way or that way. Okay, how many ambiguous parsings are there? It will tell us that kind of parsing. Okay, so what is parsing? Maybe you know about the parsing from your programming language course. But basically, with respect to the natural language processing, parsing refers to the task of assigning proper trees to the input strings. Okay. For example, book that flight. Book that flight. Okay, so the parse tree is going to be sentence, verb phrase, noun phrase. Noun phrase is going to be determiner and noun. Determiner is that, noun is flight, VP is V, and this is going to be book. Okay, so I assign the proper parse tree to this sentence according to our grammar. Remember, our grammar was something like this: VP, NP, and VP could be verb or verb, propositional phrase, etc. NP could be noun or nominal and noun, etc. You remember that? Or NP, okay. So this is my grammar. Given the sentence and the grammar, come up with this tree. Okay. By proper, we don't mean that we solve the ambiguity. Okay. It means that by proper we mean that all and only the elements of input and is covered, and it has an S at the top. It has an S at the top, and all the words are covered. Okay, we don't have any words left out. Okay, booked that flight from Ankara. If I said this, so in this case, from Ankara would be left out. This wouldn't be a proper tree, okay, because we are not giving anything about these two words, okay. So it doesn't actually mean that the system can select the correct tree among all the possibilities. What does it mean? It means that, okay, it means that all the words should be covered. That's one thing, and this tree doesn't produce any dangling nodes. For each node, end node, leaf node, there is a word corresponding. That's what we mean by proper. Okay, so it looks like we are gonna do lots of search. Why do we need to search? Because I made it very simple, this grammar. But as you remember, I have many as rules. One of them is SVP. Okay, the other one was, okay, SNP VP, etc. So it changes. So how did I know that? I should start with VP and P thing? This one instead of those. I was lucky maybe because I need this solution maybe. But I mean, search involves testing this, and testing this. Okay, until you find all the possible trees. We should not stop when we find the first proper tree, but we should continue doing the search until we obtained all the proper possible trees. That's the meaning of parsing, and for that we are going to do lots of search. We are going to try lots of trees. We are going to try lots of combinations, and that's going to be our basic strategy. And we will be looking for most efficient ways of doing the search. And like we did before, we are going to see that dynamic programming will be very helpful for us in this case. So we will be able to do this in polynomial time, even with all the ambiguous parses. We will stay in the polynomial time. Well, it's kind of expensive polynomial time, but at least it's not exponential. Okay, so we are going to try some basic methods before we are introducing these dynamic programming techniques, which seems a little bit complicated, but they are not actually. Okay, so for the parsing, remember what we did from the beginning of the semester. What we did was we did the morphological analysis, right? Morphology. What is morphology? Morphology is the study of the words, how the words form when the derivation rule comes in. How do we handle those derivational rules? Inflectional morphology or derivational morphology, doesn't matter. We looked at them and we said that finite state transducers are good ways of doing this morphological stuff. And then after the morphology, we looked at the parts of speech for words in a sentence. Okay, that's what we did, parts of speech. And after that, we are trying to give more meaning to the sentences. We are trying to find the structure of the whole sentences. But when we are doing this, we assume that morphological analysis and the parts of speech tagging is done. So we will assume that, okay, we have all the words, we have the complete sentence. Okay, we are not doing this online, we are doing this offline. We have the complete sentence, and the input is part of speech tagged. But when I say part of speech tagged, I don't mean that ambiguity is gone. It could be for example, this, let's go there. Book could be a verb or noun, okay? So I don't mean that part of speech tagging is done eliminating all the ambiguities. Ambiguities are there. That's why the book says part of speech isn't done yet. But I know the possible part of speech for each word, okay? And we will not worry about the morphological analysis, okay? All the words are known. We will not deal with the unknown words, okay? We know that these are problematic in many ways, especially morphological analysis, sometimes a part of speech tagging in this case, but we will ignore those problems because we are trying to deal with the NLP parsing right now. Okay, so let's look at this top-down search. What do we mean by top-down search? As I said before, given a sentence such as book that flight, just very simple sentence, we are trying to find a parse tree for this one. So top-down search says that start with the non-terminal as sentence, okay? Start with as, and after that, try to grow a tree from top to down. Work your way from top to down. Here is an example. I started with an S, and my grammar says that S could happen like this: as, noun phrase, verb phrase, okay? Or S could be, this is like the flight arrives now, okay? The flight arrives now. Noun phrase, verb phrase kind of structure. Or it could be auxiliary noun phrase, verb phrase. It's like a question. Did the flight arrive? Or like this one, book that flight, okay? I don't know which one is going to be, okay? As we said before, this is like a search tree. It could be one of them, and I am trying to parse this sentence, maybe book that flight. Okay. So until at the end I find the tree that produces this three words, I should continue from this one, okay? Maybe I can go there, or maybe I can go here, okay? Or from this one I can go here, or by this, okay, maybe I should, these arrows are for the whole tree, okay? This is not just for MP. Maybe I should make it clearer. And this one can go there or there. And from this one it could be this and or that, okay? So it looks like at every level I am expanding this tree, okay? Either in 3 branches or 2 branches and sometimes more. So let's say I am expanding tree with 3 branches at every level. If I do this like 5 level expansion, so it is 3 to the 5. It looks like this is growing in exponentially. If the sentence is a long sentence, this is going to grow exponentially. So this way of doing things is not that efficient, because this is an exponentially growing tree. Let's try to find the proper tree for the book that flight. I think it's going to be this one. choose the green. Okay, green is here, and this one is going to be expanded like S VP V, and this MP is going to be noun, determiner and noun. Okay, I am going to do a little bit cheating. I am going to write the whole answer here because this is getting uglier. Okay, I'm going to do this. This verb is book, and this is going to be determiner and noun. This is going to be that, and this is going to be flight. So instead of adding 2 or 3 more levels, 1, 2, 3, yeah, okay, 1 is for this one, 2, 3. Instead of doing 3 more levels, I just wrote the whole thing. So 3 levels, 4, 5, 6 levels. 6 levels. At every level, maybe I have 3 expansions, 3 branches, 3 to the 6. As I said, 3 to the 6 is a large number for this kind of a sentence, very simple sentence. So top-down space, top-down space or top-down searching kind of works, but this is expensive. Why? Because it is producing so many trees. I have to check many things. If this number goes to 10, 11, my job is going to be very difficult. I had to produce lots of stuff. Okay, so the opposite of doing this is bottom-up parsing. Maybe it's going to be more efficient. Since, I mean, what is the problem with top-down space? It has to check all kinds of possible parse trees against these 3 words, and all kinds of parse trees is not that easy to check. Okay, if you don't have the time, if you don't have the memory, it is not that easy. So that's the problem. How about this bottom-up parsing? What am I going to do with the bottom-up parsing? Of course, if we start from the words and grow the tree from bottom to up, so I will not start from the as state. I will start from the words themselves, and I will work my way up from the words to the S. I will try to hope to find S at the top. The same sentence, book, that, flight. Okay, so for book and that and flight, I need to find some terminals. In my grammar, there should be like, I know that verb book, I know that there is a determiner that, I know that there is a noun flight, but also I know that there is a noun book, right? And I am sure if I look harder, I will find other confusing stuff for the ambiguous stuff for the noun, this flight and that too. Okay, so what am I gonna do? Using these rules, I will say, okay, book, verb. Okay, let's ignore for a minute that book could be a noun too, and this one is determiner and this one is noun. And if I continue with this part, it is nominal noun, and then this makes a NP, and then put them all together, this is a verb phrase, and I know that if I continue, there is an S, because remember SVP at the top. As I said before, I ignored this ambiguity here. I also ignored the other stuff. This doesn't go. This doesn't have to go that way. It could. I could have used other rules too. Okay. The number of trees that I am producing at the end is not going to be any smaller than the number of trees that I am producing with the top-down parsing. Okay. So I cannot say bottom-up is more efficient than top-down. They have both problems of producing unnecessary trees. For the top-down parsing, the trees that are produced are all valid trees. Okay, they are not proper trees, but they are valid trees. Why? Because they all start with an, they all come from S. Bottom-up search, some of the trees that I am producing doesn't make much sense because they don't go up, they don't grow to be a S, to be a sentence. So they have their own problems, but they are both inefficient. So we have to find a way to solve this problem in a way that makes it more efficient. Well, I mean, this is the problem at hand. I mean, I cannot be as efficient as a linear time system, but we are gonna see some stuff. We are gonna notice some stuff saying that, okay, why do I have to do this over and over and over again? For example, let's go to the other one. Okay. Why do I have to produce this NP that nominal over and over and over again for the same words? Okay. If I know that I can produce that part of the sentence a subtree, I can store that information somewhere and I use it again. That's the idea of dynamic programming. Remember the place that we use the dynamic programming 2 times. The first time was the edit distance. We said that, okay, with the edit distance, I can match the beginnings of the words and I can keep that information in a table. Later I could use that information to match the rest of the words, right? That's what we said with the edit distance. Also, I did the same thing with the part of speech tagging. We said that I could store the assignment information. I could store the assignment information up to some word somewhere, and later when I do the assignment, when I continue the assignment for the rest of the sentence, I can use those that information. And we are going to do the same thing with the parsing too. Subword information, sub-sentence information, for example, that flight is a noun phrase. That flight is a noun phrase. Once I find that, I could use that information. I could keep that information in some place in my table, and later when I need it, I can use it to make larger trees. That's the idea. So we are not going to solve the same problem over and over again. It's going to save us lots of time with the dynamic programming. Okay, good. So again, top down and bottom up. The only searches for trees that can be answers. So all the trees are always valid. They all have the S's. Bottom up, only form trees that is consistent with the words. So many of these trees are not consistent with the words. Okay, many of these trees, they will not lead to S's. Okay, they are working on 2 different spaces. So what are their problems? It suggests lots of trees that are inconsistent with the words. Okay, and this one suggests lots of trees that makes no sense globally, that are not going to lead to an S. Okay. Okay, so what are we gonna do? Okay, the thing is that if you do a stupid backtracking, that means that try everything together. If it doesn't work, backtrack and try the other one. Try something. If it doesn't work, try the other one. Remember our tree It could be as in 3 different ways, as noun phrase, verb phrase, as verb phrase, as auxiliary verb phrase, noun phrase. Okay, so it's like try this and try that and try that. If it doesn't work, then expand it again, do a breadth first search kind of strategy. And if it doesn't work, go back and try that one. If this doesn't work, go back and try that. If it doesn't work, go back and try that one. This is called backtracking, but backtracking, if it is applied this way, is too expensive. Okay. The other thing is ambiguity. As I said before, I mean, if we are lucky, I would do this as VP and book. Let's say our sentence is a single sentence. If I am lucky, then I will follow this path and find the solution. But the thing is that finding a single solution, finding a single parse tree is not enough. I have to find all the parse trees because there is ambiguity, and I know that there is ambiguity, and I know that ambiguity will cause many different paths. Maybe there is another solution here, and maybe there is a third solution there, and I am supposed to find all of them. And I am supposed to find all of them. So this is ambiguity. Shared subproblems we already know. Okay, we are going to look at them one by one. Whatever we do, we shouldn't forget about the ambiguity. Ambiguity is this. We already know that. Okay. Let's do the same thing again. Let's resolve this ambiguity in Turkish. Translate this sentence in Turkish and to Turkish and say the same sentence in Turkish too. I shot an elephant in my pajamas. I shot an elephant in my pajamas. What is this in Turkish and what is this in Turkish? On the left. Anybody?
Soldaki pijamalarımla bir fil vurdum değil mi hocam? Ben pijamaları fil pijamaları giyerken.
Say that in Turkish again. Tell me the complete Turkish sentence.
Pijamalarımı giyen fili vurdum.
And what is on the right?
Pijamalarımı giyerken fili vurdum.
Pijamalarımla bir fili vurdum.
Evet.
This one is pijamalarımı giyen bir fili vurdum. This one is pijamalarımla bir fili vurdum. I think this is from a famous movie or some comedy. I shot an elephant in my pajamas. I looked it up. And I think usually, okay. There is another third meaning. See, this guy is wearing a pajama and there are elephants on his pajama. So actually, one morning I shot an elephant in my pajamas. How he got in my pajamas, I will never know. Okay, so this guy, American comedian. So the second sentence is kind of giving me the context. Now I know that what he means is the first three, right? First three. But so this is an elephant wearing a pajama, right? Wearing a pajama. And this guy, okay, this elephant is wearing his pajama and this guy is shooting it. That's okay. So again, we have seen many examples of it. Whatever we do, bottom up or top down, we shouldn't stop when we just see this tree. because it could be this 3 too. So how are we gonna know what were the ways of handling ambiguity? One of them is just ignore it. Okay, get the first one and continue. The second one was find all the ambiguous solutions, all of them, and report them to the upper stage, which is semantic analysis. With the semantic analysis, we will figure it out. And the third one, remember the third one? Third one was try to keep the ambiguity in. Like, I mean, if you are translating from German to English, maybe you are gonna keep the ambiguity in German, and it will be exactly the same ambiguity, and that will be fine, right? But if you translate it from if your job is translation from English to Turkish, I cannot keep this ambiguity because I have to translate this differently than this one to Turkish. So I have to find this ambiguity. Okay, so shared subproblems is already there. We talked about this, shared subproblems, because we said that many times we are gonna do, I mean, especially for the long sentences, some parts of the sentence we will keep on them, and we will be doing the same sub-part trees over and over and over again. So if you do the naive backtracking, this will be duplicated work. So let's not do it. That was the idea. So let's look at this noun phrase, a flight from Indianapolis to Houston on TWA. Okay, this is not a complete sentence. Okay, this is just a noun phrase. But if I am working on this sentence, it's a noun phrase, a flight from Indianapolis to Houston on TWA, 6-8 words in this noun phrase. Okay, I know that on TW is a propositional phrase. I know that to Houston is a propositional phrase. From Indianapolis is a propositional phrase. There is no meaning to, when I do the backtracking, there is no meaning to assign PP to these words over and over and over again. Okay, that was one example of shared subproblems thing. Either you are doing bottom-up parsing or top-down parsing, you will end up doing the same propositional phrase generation, whatever tree branch you are on. Why don't I keep this information somewhere? That's the idea of dynamic programming. Or the book gives me another example. It says that nominal could be noun, or nominal could be nominal propositional phrase. I am going to have the same problem again. My second monitor is going to shut itself. Let me do this. Maybe it will. My second monitor thinks that I am not using it. Okay. Or maybe I can do this. Open the menu and close the menu, and I used it. Okay, so this nominal noun or nominal recursive one. Okay, and if you choose to apply these rules, okay. So remember our top-down strategy. If I have a nominal, it could be either noun or okay. Let me do it this way. Nominal noun or nominal PP. Okay, so which one am I going to follow, this one or that one? Usually when I do the breadth first search, I would choose this one first, and if it doesn't work, I would come to this one. So if I start doing this, always start doing this, I will have to do this. Okay, noun phrase, a flight, nominal noun. But if I do that, a flight from Indianapolis to Houston didn't work, okay? So I have to backtrack, okay? I do this, okay? Nominal and propositional phrase. Nominal, okay? From Indianapolis. But this didn't work because I am not producing a nominal tree, and I'm backtracking and doing this, and I am backtracking and doing this. When I backtracked, I didn't have to do these over and over again. Okay, so shade sum problems is a common thing for both top-down parsing and bottom-up parsing. Good. So we are gonna use again dynamic programming to solve these problems, and I'm going to give you two methods that does the dynamic programming. CKY is a bottom-up dynamic programming approach. Early parsing is a top-down bottom-up approach. In terms of efficiency, they are almost the same. They are in polynomial time. I am going to show you the algorithms for both. So we are going to calculate the timing analysis of both algorithms. But it is polynomial time in terms of basic operations. If you have a very large vocabulary and lexicon, well, it is not that small polynomial time number, but anyway, it is not exponential at least. And these two will avoid the repeated work. Okay, so I will only avoid the repeated work. I will not ignore some possible parsing strategies. Okay, so I am going to efficiently store ambiguous structures with shared subparts, and ambiguity will not be resolved. Ambiguity will be there. I will not solve it. All I'm going to do that this parse tree is parsed with 2 or 3 parse. This sentence is parsed with 2 or 3 possible parse trees. That's what I'm going to say. So let's start with CKY parsing, if there are no questions. Are there any questions up to now? Are there any questions? Okay, if there are no questions, then I will start talking about CKY parsing. Where does the CKY name come from? It is the inventor, the first, the letters of the names of the inventors. Okay, whoever wrote the paper, people name them after those people. Okay, CKY parsing is a bottom-up parser, but it says that I am a context-free grammar parser. Yes, that's true. And but I need my rules in this way. It's going to be binary rules. These are called binary rules, and it's going to be epsilon free. Okay, what do I mean by this? Your rules are going to be like this: sentence, noun phrase, verb phrase, or verb, for example, book. That's it. You are not allowed to have any other rule types. For example, this is okay, but this is not okay. Auxiliary, okay. Noun phrase, verb phrase. This is not okay. Why? Because this is not a binary rule. This is not okay. Okay. So I cannot do that. Or this kind of stuff is not okay. A goes to A, B. This is a terminal, this is a non-terminal. It's not okay. And the reason why they had chosen it this way, okay, there are two things to talk about now. The first thing is, what am I going to do with this rule? The answer is, there is a way of converting these kind of rules to these kind of rules. And we can deal with it, and you're going to see in a few minutes. The second thing is, why do we need to have rules like that? I mean, why do we need to convert our rules to something else? The answer is this. Okay, the book gives the answer that way. The book says that let's look at this rule. And this is not a regular grammar or anything like that. But if I have a rule like A, B, C, both of them are A, B, all three of them are terminals, non-terminals. If there is an A somewhere in the input, there must be B followed by a C. Okay, that's what we know. If A spans from I to J, it's like this. Let's say these are my words. Okay. And if I have A, B, C. If A spans from I to J, let's say this is position I and this is position J. This one says that there must be a K somewhere between I and J that will separate these into two. And this part will be B, this part will be C. So in order to be able to produce this A, I need to find this B and C. And how am I going to find it? I will make a search on this K. K is going to change from I to J. For each possible K value, I will try to see if there is a available B and if there is an available C. If these are there, then I can produce an A. Okay, remember this is a bottom-up parser. Okay, this is a bottom-up parser, and bottom-up parser comes from this side, from B to C side. Okay, so I am going to, for each rule application, I am going to make a one-dimensional search, and each search will produce me all possible rule applications. Okay, so the idea is, if I apply, okay, for this kind of rules, there is no problem. I don't need to make a search. It is already there. For this kind of rules, I need to make a search before finding out if this rule is applicable or not. Since I am coming from bottom to top, I already know these are applicable. At the bottom, at the very bottom, I have the words, I have my lexicon. Okay, that's the basic idea. Okay, any questions? Any questions so far? Okay, if there are no questions, then let's take 10 minutes of break. After the break, we will continue. So let's be here around 14:22. For the newcomers, our midterm is next week. Okay, if you did not make it to the beginning of the class, our midterm is going to be, this is chapter, okay, 13. Let me put it here. Okay, midterm exam is on December 7th, 2020 at 13:30, and we are gonna start our lecture at 32. Okay, see you in 10 minutes. Evet. Evet. İnşallah. Peki olur. Okay, people. I think I was 13.
Hocam devam etmeden önce bir şey sorabilir miyim?
Sure.
Şu anki assignment'la alakalı hocam. İkinci assignment'la alakalı.
Ask it in English.
Okay. The wiki dump you have sent in the assignment description has some problems in it. It has like styling tags, CSS words in it, like alignment and width, height, lots of English words.
Yes.
And also it's not constructed with sentences, like they don't have.
So are you asking me, can you use some other data set?
Yes.
Okay, yeah, sure.
Okay, thank you.
Or if you like, you can play with the data set.
Okay, it's a fairly large one, so editing can take some time, computing time.
Well, eliminating those kind of things automatically is not a difficult thing, but I mean, if you like.
Okay, thank you.
What are you gonna use?
I'm going to use NLT case, the Natural Language Toolkit Libraries Brown set.
That's
Brown data
it's
set.
Turkish, right?
It's English data set.
No. I need Turkish. That's why I need to give you.
Okay, I can find the Turkish one.
I think somebody asked me the same question. I think somebody found a better data set. I mean, better in terms of these kind of formatting issues. Who was that? Somebody asked me that if I could.
I think there's a Turkish Wikipedia dump with better structuring in kaggle.com.
Okay, use that one too. Okay, I need something Turkish.
I think İlhan Hoca knows another one. Maybe he can share it with us.
Okay, if you want, I can share.
Okay.
Okay, that would be amazing.
Ilham, why
Thanks.
don't you share it with the whole class?
Okay, sure.
Okay,
Professor.
post it to the Moodle page or Teams page.
Sure. I'm gonna do it now.
Okay, that's good.
Thanks.
So okay, let's go back to the CKY parsing and let's dive into the algorithm. Okay, but what did we say before? We need this binary rules, and let's look at the binary conversion. That kind of a structure is called Chomsky normal form. Okay, so binary rules like this kind of rules, these are called Chomsky normal form. Remember Chomsky? Chomsky hierarchy. Chomsky defined this kind of a context-free grammar, and any context-free grammar could be transformed to Chomsky normal form. Okay. The problem is this. Okay, we are gonna change our grammar in a way that it becomes a Chomsky normal form grammar. Now, so, I mean, our derivation trees will be different than the original grammar, because in our derivation trees, there will not be any S rules like that. And it might be a problem. Well, it's not a very big problem because we can always go back after, of course, the tree is parsed. Okay, so as I said before, Chomsky normal form is this. Okay. Either it is a as a rule of context-free grammar. Remember the context-free grammars. On the left there should be a non-terminal. On the right there should be a non-terminal terminal combination. But Chomsky normal form says on the left. Chomsky normal form says that on the left there should be a non-terminal, and there should be two non-terminals or a single terminal. Okay, so this is the binary rules. That's what we are going to do. Example, if I have a rule like this, SABC, which is not in binary form, Chomsky normal form, I introduce another dummy, okay, extra non-terminal x goes to AB, and I replace this AB with x. Okay, so these two, this one, the original one, single rule, and these double rules will accept exactly the same strings. Of course, their trees will be different. Okay, their trees will be different, but they will accept the same strings. Okay, and this x is a completely brand new non-terminal. It should not occur anywhere else in my grammar. That's why we called it x. So you will need to make up new non-terminals when you are doing that kind of stuff. So what else could happen? I mean, we talked about that. What else could happen? Let's say I have something like this. AB. So A is of course non-terminal. A and B are terminals. We don't allow this. What are you gonna do? Of course you're gonna do this. A, x1, x2, x1, A, x2, B, right? So you can always find these kind of conversion rules. You can always find these kind of conversion rules if you have such stuff. Because on the right side there is no contextual grammar says that on the right side there is no rule. I could have things like A, B, C, D. Okay, capital letters are non-terminals. Small case letters are terminals. Okay, so I can always. So how am I gonna do that? I can do it in a way where I can introduce two. Okay, like that. This could be x1. This could be x2. Of course, x1 and x2 will not work. Inside the x1, maybe I can take this to an x3. This one is going to be x4. So x1 is going to be x3b. x2 is going to be x4d. And x1 is A, x4 is C. See, I mean, it might get a little bit complicated, but it is not actually complicated, but a little bit detailed. But there is always a possible solution, and this could be done automatically. So that's called binarization, and there is a nice algorithm to do this binarization. After the binarization is complete, we can do our CKY parsing. So we are going to do this grammar, L1 grammar. Remember this, because I cannot go back and forth with this grammar. I don't know what am I going to do with this, but how am I going to do this? Keep this at some part of the screen, because I will keep doing this back and forth. Remember, there are 3 S's. SSS. Okay, noun phrase, verb phrase, auxiliary noun phrase, verb phrase, and verb phrase. And then I have noun phrases. I have the nominals. On the right, I have the lexicon. What is lexicon? Are words. Okay, my nouns. See that book is both noun and a verb. My pronouns, proper nouns, auxiliary. Of course, it's a very simple grammar. For the auxiliary, I don't have any do, I don't have any did, have, etc. Can, right? And propositions are not like that, but just a demonstration. This is not a complete grammar. I mean, for the complete grammar, you need hundreds of rules, sometimes thousands of rules. This is just an example. Remember this nominal thing, the recursive nominal thing. Okay, this recursive nominal. That was the complication of the noun phrases, and backtracking is going to have very serious amount of time. It will be problematic for the backtracking because of this recursion, right? Okay. For the verb phrases, this propositional part is going to be problematic, because with the propositional phrase there could be a noun phrase. With the noun phrase, now I have the nominal again. At the end of the nominal, I have the propositional phrase, a longer recursion. So we need to be able to handle all of these. So straightforward search is going to take lots of time, lots of repeated stuff. But with the dynamic programming, we are going to handle these. Okay, so remember this. Let me try to open this with a browser. Yeah, I'm going to open this with a browser. And what is this? 30. Okay. So if we need to, I can go to this one and come back again. Good. Okay. So let's apply this rules, binarization rules. Remember, some of them are very bad rules for us. For example, we don't like this. We don't like this. Okay. How about then? We don't like this. We don't like this. This is okay. No. Okay, okay. Okay. This is the, we don't like it. We don't like this one. And these are all okay, right? These are all okay. So for these, the ones that I marked with an arrow, we have to do the conversion. Okay. This one, I already told you. How do you solve this one? We don't like it. How are we going to solve it? How are we going to convert it? Instead of doing this one, I could say VP. What is VP? Okay, this is good, right? Verb, noun phrase. Okay. S, verb, PP. Okay. I handled this one and this one and S, VP, PP, and this one. This one is bad and this one is bad. I think it makes sense to come from the bottom to the top. So let's handle these. For example, this one is bad. Let's handle, I know how to handle this one. Let's look at this one. Let's take this. How do I handle this one? Verb. Okay, so I'm going to do this. VP and book, or include, or prefer. Okay, so I handled that one. See, it was nice. So since I handled this one, I can put this VP to the S, and S can go to book, include, prefer. Okay, so that's how I handle it. So the book already did that conversion, and instead of doing this one by one with our hand, let's do it that way. See, it is handled that way. How many new non-terminals are introduced? That one, that one. Two of them, right? Just two. But we have many more rules. Like, what are those rules? Many S's, right? And I guess many VPs too, right? That too. Okay, let's look at them one by one. Did not change. This one changed because 3 is not a good thing. X1 and X1 works that way. SVP, we don't like it. Why? Because it has to be either binary or this VP has to be a terminal. So these are the terminals. These are the binaries. So where does this come from? This one comes from like this one, right? It one corresponds to this one. So VP can be that. So we were lucky there. So where does these 3 come from? These 3 come from this verb, but verb goes to where does the verb go? Verb goes to book, include, and prefer. And I think I did not put everything in here. Some of things are missing. For example, where is noun? Lexicon is missing. I mean, this one, this, verb, okay, I am going to include everything here in this place. Okay, so I should include all the lexicon rules here. Okay, and these are coming from the lexicon rules. Good. So we did an example on binarization. Okay, let's look at the CKY algorithm on how we use the binarization. So let's build a table so that an A spanning from I to J in the input is placed in cell ij in the table. So remember the discussion at the beginning when we say A goes to B, C. All of our rules are like that now. Okay. If A is going to correspond the word's position from I to J, okay, then this BC should separate this word range into two, from I to K, from K to J. Okay, I to J, then there should be a K in between. And if I have my B and C at my hand, then I would say that if there is B and C, B is covering the words from position I to K, and C is covering the words from K to J, then I can put in box IJ a non-terminal A. Okay, so that's the idea. So I will have boxes like a two-dimensional array. It's kind of half of two-dimensional array. I will have boxes, and each box will represent the words between I and J, the position I and J. Okay, position I and J. And in that box, I am going to put all the non-terminals. For example, it's going to be like this. It's not going to be exactly like that, but this is 0, 0, this is 0, 1, this is 0, n. Okay, so this 0, 1 says that 0, 0 doesn't make any sense, so I am going to ignore this column. So 0, 1 says that what kind of non-terminal can I put between the words and 0 and 1. So book that flight, book that flight early. Okay, so what kind of things can I put in 0 and 1? Book is either, okay, let me try to write this smaller so that, okay, this is 0, 1, this is 0, 0, 2, 0, 0, 3, 0, 4. Okay, so this could be a verb or noun, right? Because my rules are saying that. Okay, this is like that. This is 0, 2. What could happen with 0, 2? Book that. I don't see anything. So what I'm expecting is I should find an S at the end of this operation at the right top corner, because this S covers 0, 4. Okay. Here I have 1, 2. Here I have 2, 3. Here I have 3, 4. Okay, that is a determiner, so I am going to put a D there. Flight is a noun. Early is, I don't think that I have early. Early is do I have a, okay, preposition maybe, PP. Okay, so it looks like I don't need the bottom half of this. I don't need this part. I don't need this part. So I took them out. I am going to fill in this table starting from these words. Okay, this is 0, 1, between the position 0 and, okay, think it this way. Think it this way. This is position 0, 1, 2, 3, 4. Okay, between 0 and 1, I can get a noun and verb because there is book there. Between 1 and 2, there is a determiner. Between 2 and 3, there is a noun flight. Between 3 and 4, there is this prepositional phrase. Prepositional, not preposition, just preposition. P. Okay. Preposition P. Okay. Now I am going to do this kind of thing. What can I put here between 0 and 2? Well, this 0 and 2 could happen like that. Can I do something with verb and determiners from 0, 1 to 1, 2? See? This is, now I am trying to find I to J. I is 0, J is 2. Can I do something between 0 and 1, 2? So it is going to be 0, 2. Can I do something V and D? Okay. Or noun and D? Can I do? Is there such a rule? No, I don't find any rules like that. But I think I can do something like this. Can I do something? This is, what is this? This is 1, 3, right? With the 1, 3, from 1 to there is the determiner. This is determiner. And from 2, 3, there is noun. I think there is a rule on the left side, there is determiner and noun. That's called noun phrase. So I can put a NP here. Okay. So this NP says that between 1 and 3, I can cover this. So I solved it. So whoever needs this NP can use it from now on. I don't have to come back and discover this again. Okay. So remember, I kept saying always we are gonna reuse the position dynamic programming. So this is our dynamic programming table, and each cell we put whatever we discovered, and we are trying to go to the top right corner, and we are trying to hope that there is an S, there is a sentence at the right top corner. Okay, so that's the basic idea, and it looks like this complexity is kind of number of words squared, because we are filling a table of 2 dimensions, and this is an n by n table, although half of it, but it is still n squared. But for each box I have to do a search between the I and J, and a cube comes there, but then I have to scan all the rows in some position. That's going to make it a little bit more expensive, but that's the idea for the CK by parsing. So after I give you the idea, let's go back and let's try to give you the main algorithm. We are going to build a table so that an A spanning from I to J is in the input is placed in cell IJ. So for each possible span in the sentence, there will be a cell in my table. Okay, and hopefully at the cell of 0n, at the end we are going to find an S, and that S is going to be our sentence. And if we build the table bottom up, we will know that the parse from A must go from I to K, and from K to J for some K. Okay, so to put elements in a single box, we need to make a search between I to J, so that is there such a rule? A is I to J, right? Is there such a rule as I to K and K to J? Okay, so in terms of rules, this is exactly what I said. If I have a rule like that, if A is going to be from I to J spanning, then I need to find a B and C. B is spanning from I to K, and C is spanning from K to J. Remember always, we are coming from bottom up. Okay, we are coming from bottom to, we are going to the top. So B and C are supposed to be available. At the very bottom, we have the words, right? We have the words, and the words are going to be there. Okay, and we are going to, so for each, remember I said that we are going to search for K, okay, for all possible values of K from I to J. For each K position, we are gonna scan all of our rules, and if the rules are hundreds of rules, then that inner loop is a very expensive rule. Inner loop is a very expensive loop. Okay, good, we talked about it. So to fill the table loop over the cell ij in a systematic way, what are we gonna do? For each cell, loop over the appropriate K and look for the appropriate matches in our rules. And this is the algorithm actually. That's it. I mean, the whole algorithm is this: loop, loop, loop. J is from 1 to length of the words, and I is from J to 0. So if, let's say, if the number of words is n, this is n, this is potentially n, and k is potentially n. So it is like O n cube. But this one is kind of complicated. There are scanning of the rules all the time, and it is like n cube times, let's say, m. M is the number of rules in our data set, in our grammar, context-free grammar. So it is in polynomial time, kind of a high order polynomial time, but again, it is better than exponential. Remember our top-down search stuff? Our top-down search was doing like, if the number of levels is like k, is 3 to k, it's exponential. Even for a 3-word search, it was like 3 to the 6 or something like that. Okay, so this one is much better than that. This one is n to the power 3 polynomial. This one is exponential, 3 to the power of k, and k depends on the number of words. Okay, let's go back and let's do this. Let's try to see how it works, because I showed you kind of how the algorithm is going to work. And this one says that from j is from 1 to length of the words, and we are going to fill in this table. Okay, for the outer loop, remember how our okay, I'm going to draw this table, but I am not going to draw the lower part. It's going to be like this. Okay, so that means that I have 1, 2, 3, 4, 5 words. Okay, and this is W1, W1, W2, W3, W4. Why don't I write a complete sentence? Why do I need to write these stupid W's? Book that flight. Book that flight through Houston. Okay, book that flight through Houston. So, but remember what I told you? 0, 1, 2, 3, 4, 5. This is box 0, 1. Okay. So at the beginning, I have this J from 1 to length. It will start from 1 to length. It says that table J minus 1J. Okay, J minus 1J is this. 0, 1 is this. Should be this. Can anybody tell me what this line is? What does it say? J is going to change from 1 to length of the words. Sentence from 1 to 5 in this case. So what does this line do? Just a small hint. It's going to be 0, 1, then 1, 2, then 2, 3, then 3, 4, 4, 5. So I am filling in. Let me write those. So this is 0, 1, 1, 2, 2, 3, 3, 4, and 4, 5. So somebody tell me what this line does. I have been talking straight without stopping for the last 40 minutes. The last time you talked, it was a question about the homework. Okay, I am waiting. If nobody answers, I am going to pick somebody random.
Can I try to answer it?
Sure.
Won't it be actually going to fill in the non-terminals?
Non-terminals, yeah, exactly. It says that if what is verse J? What is verse J? What is verse 0? What is verse 1? Verse 1 is this. Okay, it's like an index. Verse 1 is this. Verse 2 is this. And verse 5 is this. Okay. Are there any rules like a verse 1 book? Of course there is. Why? Because I know that here, noun and verb. This one, noun, book. This one is verb, book. Right? Okay, so I am going to, in that case, put these in there. Okay, don't put the rule, but the non-terminal there. So put noun and verb in there. Okay, And this is the first iteration. In the second iteration, I am going to do this 1, 2, that. Are there any rules that has that on the right side and on the left there is a non-terminal? Of course there is. What is it? It is determiner, right? So this one is going to be determiner. And this one is going to be noun. This one is going to be preposition. And this one is going to be noun. It looks like all the boxes have one non-terminals. One of them has two terminals. Question for you. Could there be a box at these positions that I am marking with red? Could there be a box with no non-terminal? With no non-terminals? Inside the red boxes, there are 5 of them. Could there be a box with no non-terminals in it? We know that there could be one or more, yeah, but could there be a box with no non-terminals in it? I mean, could there be an empty box after I run this line for all the j values from 1 to length of words, which is 5 in this case? Gökçe, say something.
I don't think so. I think they should be all filled.
Why?
Because I think in the grammar, all the rules kind of define a non-terminal.
Yeah, because I mean, our assumption is there are no unknown words, right? And this is our lexicon. And lexicon should cover all the words, right? So all the words should be happening on the right side of a rule. Otherwise, one of our assumptions is violated because there are no unknown words. So those boxes which I marked with the red, they all have to include at least one non-terminal. Probably more than one is possible too, yeah, but at least one has to be there. I cannot say the same thing for all the other boxes because all the other boxes, the functions are different. This one says, okay, this is 0, 1, this is 1, 2. This is, what is this? This is 0, okay, use the blue pen. This is 0, 2. Okay, this is 0, 2. In 0, 2, there doesn't have to be a non-terminal because 0, 2 corresponds to this span, 0, 2. Book that, okay, book that. This is book that. Book that doesn't have to correspond to a partial parse tree. It could be empty. And as you're going to see, it's going to be empty. Because I cannot find a rule on the right side that says verb determiner or that says noun determiner. Do we have such a rules? Do you have such rules on the right side? No. If you don't have them, okay, verb determiner, noun determiners, if you don't have them, then that means that this box is going to be empty. So let's go back to our algorithm and try to see how we do that, okay? We already looked at this line, meaning of it. And this one says that, okay, J corresponds to the rows, okay? These are the J's. This is J0, J1, J No, I'm making a mistake. No, I don't make. No. Okay. J is from 1 to, okay, changes from 1 to length. This is 0, 1. This is 1, 2, 2, 3. 1 is, okay, these are i's. These are i's, okay? I is from j minus 2 to 0. Okay, when j is 2, okay, here in this case, j is 1. Okay, so these are the i's. I is going to be 0. Okay, this is 0. I is going to be, I is 0, I is 1, I is 2, and I is 3, I is 4. It goes that way. So let's look at this one. It says that I is going to change from j minus 2 to down to 0. Okay. In this first case where j is 1, j minus 2 is minus 1. It doesn't make sense. Okay, so for this box, for this column, I am not going to do anything. But for this column, when j is 2, I is 0, this 0, 2, I should do something about it. So it looks like I am going to fill in this first, then this, then this, then this, and then that. We are going that way. First, I am going to handle this one, then this column, then this column, then this column, and this column. Okay, so J represents the columns, I represents the rows. Okay, so J is from J minus 2 to 0. K is that famous K that moves between I plus 1 to J minus 1. In this case, K is going to be if J is 0, okay, if J is 0 and I is 2, in this case I am going to fill in something in this place. What is that? It says that, look at 0, 1, okay, if J is 0 and K is 2, okay, Ij is this box, scan all the K's that are in between. Sorry, J is, I is 0, I is 0, and J is 2. K could be only 1. Okay, it says that find a rule in our data set that says A, B, C such that I have a B in IK, I is 0, K is 1, okay, 0, 1. Find a B in IK and find a C in KJ, okay, and both of them put together, and I will put an A in there. Okay, so it is not going to happen for this box, but for later stuff it's going to happen. Okay, let's try to find it actually. So I didn't find anything when J is 2. Let's make J 3. It's going to be like this. Can I, what is the index for this? What is the index for this box? Can somebody tell me the index for this box? What is the index? Gökçe, other than you, nobody is listening. Just tell me what is the index for this box.
1, 3.
Okay, 1, 3. So 1, 3 means that I am going to scan from 1 to 3 between these two. That flight, Are there any rules that says on the right side there is a determiner and there is a noun on the right? Yes, there is, right? What is that rule? That rule, determiner noun, that noun. Where is that determiner noun? Yeah, this is determiner nominal. The problem is this. The problem this is not a binary grammar. Let's look at the binary grammar. Okay. The binary grammar for the nouns, determiner nominal. Okay, see, as you see, there is a determiner nominal. This one. Oh, okay. See, I don't have any nouns in my new rule set. All I have the nominals. I don't have any nouns, right? Noun is eliminated. So determiner nominal is replacing that one. So I'm going to put what is determiner nominal again? Determiner nominal is noun phrase. Okay, I'm going to put a noun phrase here. By the way, this is a nominal. There are no nouns anymore. Okay, so I filled in this one. How about this one? This one index is 0, 3, right? So for the 0, 3, how can I form the 0, 3? It is either, okay, for the 0, 3, how many K's are there? For this box, how many K's are there? Let's look at the algorithm. For this box, how many K's are there? K, the letter K, I mean this one. Again, I is 0, J is 3. How many K's are there? K is going to, I is 0, J is 3. K could be either 1 or 2, right? So there are 2 K's. Those 2 K's are going to do this. Can I make from 0 to 1 and 1 to 3? Okay. Can I make a rule verb noun phrase? Okay. Is there such a thing as verb noun phrase? Verb noun phrase or nominal noun phrase? Okay. When K is 1 or when K is 2. Well, this is not going to happen because this box is empty. So the only thing is these. Is there such a rule? Verb noun phrase? Let me try to find it. Verb noun phrase. Yeah, it is here. See, I found a sentence. Let's me put a sentence in here, okay? Are we done? We found a sentence. What are you guys saying? So the book that flight. See? Book that flight is a sentence and I found it. Is my parsing over? Gökçe, you don't say anything, okay? Somebody else has to say this. Is my parsing over? I found an S. Book that flight and it seems logical. Is my parsing over?
I don't know.
Salih doesn't know that. What do you mean? Say something. Maybe you may not know it, but by you don't know, you are not sure, or
I'm not sure. Yeah.
so what is your What is your doubt? What are you not sure about? Anybody else? Come on, it is not that hard. Just say something.
There is also x2.
Oh,
the
there is
previous
also
table.
x2. I could put an x2 in there too. You are saying that. Let me. Okay. What is x2? What is x2? Verb noun phrase. Yeah, x2. I could put an x2 in there too. But okay, that's a good eye. Okay, x2. But here I'm asking the same question. I found an s in my table. Is my parsing over? I found an s. Isn't that the whole meaning of bottom-up parsing? Trying to find an s. I found an s, and when I look at this one, 03, book that flight. Come on, it's not a trick question. It's an easy question. I'm trying to make you guys talk. Okay, Gökçe, back to you. Nobody's listening today.
Well, our sentence didn't finish, so I think we have to keep on looking.
Yeah. I mean, remember what is the definition of proper tree? The definition of proper tree is our tree should cover all the words. I did not cover all the words. How about that through Houston? Okay. I only covered the first 3 words. The 4th and 5th words are not covered yet. So what are we going to do? We need to keep going. I mean, this is not a proper parse tree. It's a nice tree, but it's not a proper tree. We need to keep going. So you see the idea. You see idea is each box is a position for a different k in this algorithm. And this algorithm says that for each k, try to find 2 non-terminals in the same table. Okay. For example, for this one is 1, 5. 1, 5. Okay. K is going to take 2, 3, 4. Okay. 3 places. You're going to combine either this one, okay, this one with this one, or no. This one, 1 to 2 to, then 2 to 5 with this one, or this one, okay. This is 2, this is 3 to 1, 2, 3, okay, just a minute. 1 to 2 and 2 to 5. Where is 2 to 5? It is here, 2 to 5. Okay. You are going to do this one, or this one, or that one. Okay. This one, that one, or that one. So 3 values of k. You are just combining them, trying to see if you have such rules in there. Okay. So when you come there, you're going to try this one with these 2, okay, or these 2, or these 2, or these 2. If they bring up some s non-terminal in there, then we should be fine. I found an s at the top right corner. Okay, I found an s top right corner. We can have more than one s's, s1, s2, because our sentence could be a ambiguous parse tree sentence. In that case, we are going to have 2 ways of producing the same sentence using this tree. Okay, let's take 10 minutes of break. After the break, we will continue and we will finish up with this chapter. Let's be here around 15:40. Okay, our midterm again. Here, our midterm is going to be on the state. Okay, see you in 10 minutes. Okay. Okay. So CKY parsing works that way. It is in polynomial time. So when you say it's a parser, what kind of parser is it? I mean, what did we say about the parsing? Parsing means that we assign a tree, right? Where is the tree? When you look at tree, you don't see the tree. To see the, remember we had the same problem with the dynamic programming when we first did the edit distance. Edit distance, if we implement it in the most naive way, it says that the cost of editing between these two words is 5, but it doesn't tell you how many insertions, how many deletions, how many replacements I am going to do, right? Or where I am going to do those kind of processes. It's the same thing here too. It just says that I found a sentence. This sentence is parsable. Yeah, where is a tree? It doesn't give me the tree. So to find the tree, I need to keep some pointers, and we are going to see it in a few minutes. Okay. So is this really a parser? Yeah, it's a parser. But when I say parser, I need to keep pointers like this. I'm going to show them with the green. For example, this NP, it is NP because it is connecting these two. This S is a S because it is connecting this NP with a verb. So this verb here and this NP there. Okay, so I have to keep these kind of pointers. And in that case I can go back and form my tree because S is going to be connected with 2. So it's going to be a binary tree, right? It's going to be a binary tree. Why? Because our rules are binary, or there is a terminal. That's it. Or either a leaf node or a binary node. Then it's going to be a binary tree when we are done. Okay, so what did we achieve? Okay, we achieved this without solving the same problem over and over again. Without solving the same problem over and over again, we found a dynamic programming solution that uses the subpart solutions to find the whole solutions for the whole problem. Okay, so we arranged in a triple loop, and that triple loop first scans the words from left to right, and then when we are doing this scanning from left to right, we are filling in those boxes from bottom to top. So the idea is like as I have drawn before, like this. So first I am going that way, then that, and that. That's the idea. So one way is I, the other way is J, and then for each position I am checking the K. Okay. So left to right is a good thing because our words are written left to right. So kind of online without looking at the last words. I mean, as soon as we started receiving words, this algorithm can start working. Okay, so this is one parse result. See, we missed something here. I only said that this is noun and nominal. This is noun and verb, but book by itself is a sentence, right? Book by itself is a sentence. Also, it's a verb phrase. Okay, So this flight is a verb phrase. Book the flight is a verb phrase. As you see, this one is empty. What is this one? 2 to 4. Flight through. Doesn't make any constituency. Okay. But the last column is very busy. It just says from 2 to 5. 2 to 5 is flight through Houston is a nominal. Through Houston is a propositional phrase. The flight through Houston is a noun phrase. Okay. But this S, we don't know where it comes from. Okay. Can somebody tell me where should I connect this S? Tell me the box numbers. S, where does it come from? I think it is this verb phrase and this noun phrase, right? This is S. S, verb phrase, noun phrase. Book the flight through Houston. NP is the flight through Houston, and book is a verb phrase. It's like that. Okay, good. Any questions about the CKY parsing? Bottom-up parsing, it started from the words and it goes upstairs like that. Okay, it looks like there are no questions. I'm sure I will have some questions about this next week, and we'll see it. I think as an exercise, the book fills in this last column. Of course, I already did that. Now I'm going to do this 3-5 thing. Again, 0, 1, 2, 3, 4, 5. 3-5 is through Houston. Okay. Preposition, noun phrase, proper noun. Do we have such a rule thing? Okay, let's go to prep NP. Okay, prep, proper noun. Prep MP, do we have prep empty? Yeah, PP. Preposition MP, so I can put a PP in here. PP in there, right? And I didn't find anything else. This one is, it looks like it is nominal. Where does the nominal come from? Nominal, 2 to 3, nominal, and 3 to 5. Where is 3 to 5 is nominal proposition phrase. Is that a nominal propositional phrase is something? Yeah, it's a nominal, yeah. See this rule? That rule, nominal proposition phrase is a nominal. Okay, so it goes that way, and I already did that. I did that too. Okay, this is noun phrase, and then okay. See, there are 3 sentences. Do you see that? S1, S2, and S3. S1 is book the flight through Houston. I understand that one. S2 and S3 are kind of the same because X2, remember X2 is a new name for a VP. Remember that there was a problem with VP? Right? Let's try to translate these S1 and S2 into Turkish. S1 is, here I have a verb phrase and noun phrase. That noun phrase is the determiner and nominal. That book the, okay, this nominal is going to be flight through Houston. This is S1. Let's look at S2. S2 is VP and PP. VP is here. It is book the flight. And PP is through Houston. So it looks like this sentence is an ambiguous sentence. Okay, translate S1 to Turkish and translate S2 to Turkish. Book the flight through Houston. Book the flight through Houston. Is somebody typing something? Because my chat window doesn't work today for some reason. I don't know why. I sent a message test. Did you guys see it?
Yes, we can see it.
Just you type something. Can you type something?
They typed something about 14 minutes ago.
I did not see anything. No, I did not see anything. All I am seeing is my test message. That's it. So, translate these two sentences to Turkish. The first one.
Houston'dan geçen bir uçuş rezervasyonu yapmak tarzı.
Houston.
Houston'a aktarmalı bir uçuş rezervasyonu etmek.
Houston'dan geçen bir uçuş ayır. Book the flight through Houston. Houston'dan geçen Houston aktarmalı bir uçuş ayır. Değil mi?
Evet.
Houston aktarmalı bir uçuş ayır. How about this one? This one is Houston yoluyla, but it is not, yani o yoluyla derken Houston'dan geçen değil. Houston ofisi yoluyla mesela, değil mi? Houston ofisi yoluyla bir uçuş ayırdı. So those are two different things, and these two things can be the parse trees, proper parse trees of the same sentence. X2 and S2 and S3 are the same thing, because X2, remember X2 is this. X2 is verb noun phrase, and verb noun phrase is a verb phrase. Okay, it used to be the verb phrase, but we changed it because remember X2 is here, verb noun phrase, part of the verb phrase. It's a verb phrase actually. So that was an extra non-terminal that we have introduced so that we can stay in binary. So there is, in the real world, there are no three meanings to this sentence. There are only two meanings. Okay, good. CKY is a bottom up. I mean, we are after these three things, S1, S2, and S3, but I have produced many stuff like these verb phrases, sentences here. I have produced lots of other stuff, and that table is very crowded, even for such a simple sentence. Okay, CKY populates the table with a lot of phantom constituents. There are constituents, but those constituents don't lead to any meaningful place, any meaningful S's. Okay, so segments that by themselves are constituents, but they cannot really occur in the sentence. Okay, so to prevent this problem, maybe we can do a top-down search, top-down approach. But top-down approach has its own problems, because now it's going to produce lots of nicely rooted trees, but those trees will not be connected to the real sentence. Okay, so we are going to do just the opposite, but again, we are not going to eliminate this inefficiency. Our algorithm for the top-down parsing is called early parsing. Okay, and for the early parsing, the nice thing is we don't have to modify our grammar. It doesn't have to be Chomsky normal form or normalized form or the binary form. Okay, again, it is based on a table, but our table is not two-dimensional, it's a single-dimensional, and the number of elements in the table is the same as the number of words. Okay, and again, this is going to go from left to right, and it's going to involve some searching, some matchings, and etc. So the table length is n plus 1, and n is the number of words. It's not a two-dimensional table, it's a single-dimensional table. And inside my table, I will have entries. Our entries will be our rules, but modified rules. I mean, by modification, I am not saying that it's a binary kind of stuff. It is just a rule that has some kind of a memory that shows where I left in the sentence. Okay, so inside the table, I have completed constituents. It says that from beginning to this, I have this constituent. Okay, from this to this, I have in progress constituent, and in this case, I am predicting a constituent. I am predicting the constituent. So three types of elements will be in the table, and let's see what kind of things they are, and that will be much clearer now. First, let's see how we are going to use our rules. Okay, our rules will not change. They will stay the same. I am not going to make up new rules. Okay, if it is binary, it's binary. If it is not binary, that's okay, no problem. We are not going to change it, but we will have these dotted rules. Okay, so when you say s.vp, I am predicting a VP. I am saying that it is possible that I will see a VP. Okay, and if I have that VP, that's going to make a sentence. This one says that I have seen a determiner, and I am predicting a nominal, and I am in between now. Okay, this is called an NP in progress. And this one says that I have found a VP. That VP is composed of V and NP. Okay, so these are the three cases for the dotted rules. Okay, 3 cases of the dotted rules, and in each cell of our table, I will have many of these. Okay, those rules, they come with the position. The sun says that I am predicting a VP at the start of the sentence, 0, 0. Okay, this one says that an NP is in progress, and I have seen a determiner from position 1 to 2. Okay, and this one says that I have found the VP between 0 and 3, starting at 0, ending at 3. So if my sentence is book that flight, again, my positions are 0, 1, 2, 3. Okay, when you say 1, 2, so that means that, let's look at this one. That means that I have found the determiner between 1 and 2, and I am predicting a nominal afterwards. Okay, this one says that I have found a VP between 0 and 3, book that flight. Okay, and the VP is composed of a verb and a noun phrase. Okay, this one says that I am at the beginning and I am predicting a VP, and that VP, once I found it, is going to be a sentence. Okay, so these are the states and locations of my rules. So these are new notation. As I mentioned a few minutes ago, I'm not going to modify my rules. The number of rules are going to be the same. I am modifying in a way that I am allowing these dotted rules. Also, I am permitting these positions. So the early parsing, the purpose or the final destination for early parsing is finding something like this. If you do S goes to alpha, okay, and dot between 0 and, then I am done. Remember, for the CKY parsing, okay, the main goal was to find an S at the top right corner of the table, right? But with the early parsing, our goal is coming to a rule like this. Okay, producing a rule like this, a dotted rule that says I have covered from position 0 to n, and I found an S. If this is the case, then I am done. Of course, there might be more than one S's in there, and that says that that sentence is ambiguous. Okay, so we are going to start from position 0, and we are going to end with position n. That means that there are n plus 1 entries in the table. Okay, new predicted states are created by starting top-down from S. So it's a top-down process. We are not going to start from the words. We are going to start from the S, and there might be more than one S. And each time we see a new word, we are going to modify our dotted rules, and we are going to move our dots from left to right. Okay, at the beginning everything is incomplete. No rules are complete. Rules are going to be completed when they have this kind of situation, and at the end we like to see a completed S rule. Okay, so this is the main algorithm. At the beginning or any time, predict all the states yet that you can up front. Then read a word. We are going to read a word, and then whatever predictions I have, I am going to see if those predictions are met. If the predictions are met, then I am going to move the dots, and I am going to produce new predictions. Okay, so I extend the states based on the matches, and I generate new predictions, and I go to the step 2 and read another word. Okay, and I am done reading all the words, and I like to see an predicted completed S rule. Okay, and this is the main algorithm here. It's the main algorithm. Early parse, I get the grammar and the words, and I return a chart. So at the beginning, I put this rule, a dummy rule or new phantom rule, to my table at position 0. Okay, at position 0. And see, I have a loop that runs from 0 to length of the words. That's the main rule. And then in my chart, okay, in my chart, I will take the rules one by one, and I will say if the rule is not complete, okay, then I am going to do either one of these. If it is complete, then I cannot do anything much. Okay, it is there. But if the rule is not complete, I am going to do one of these. If the rule is not complete, it is a rule like that. Okay. And the next category of the state is not a part of speech. What does this mean? If it's a part of speech, then that means that I am done. I reached the word, okay? If you did not reach the end of the tree, okay, then I am expecting something. I am going to call this predictor function. If it is a part of speech, okay, if the next category is part of speech, then that means that I am scanning, I am completing the rule. Okay, if the rule is complete, I came to something like A, B, C dot, then that means that maybe I can go back and check whoever needs such a rule, it is satisfied now. Okay, maybe this one is not as clear as the previous algorithm, bottom-up algorithm. To make this more clearer, let's do an example from the book again. This is the predictor, scanner, and completer. Okay, completer does this. Okay, remember the completer is called incomplete, and this, so it is not incomplete, complete. Completer is called when the rule is complete. Okay, if I have something like this between J and K, then for each rule between I and J, okay, in this box, in chart J, that needs a B, then I can say that I have seen the B. See, what I do is I move dot from here to there. So I added the new element to my chart between I and K, because between J and K I have found this already, and somebody is waiting for B, okay, between I and J. Now I can put that rule between I and K. Okay, so let's go to the example. This is going to be a very simple sentence. Book that flight. It is not book that flight through Houston, because as you see, this is going to produce many more trees that are not going to be connected with the words. Okay, so we should find an S from 0 to 3. So our table is going to be like that. So chart 0, chart 1, chart 2, and chart 3. Okay, let's look at chart 0. At the beginning, what did I do? I did this, okay? Remember, that was the rule. Put this in there. It's a dummy start state. Then after that, this is our grammar, right? If you are expecting a sentence, if you are predicting a sentence, that means that you are predicting this rule and this rule and this rule, right? And then if you are predicting this rule and this rule and this rule, then you are predicting, okay, then you are predicting from the noun phrase a pronoun. Okay, from this noun phrase you are predicting a proper noun. From this one you are predicting a determiner, okay? So I put all the NPs, then I put all the VPs, okay? And of course, I need to put all the expected words, but we don't put that because that's already known. So note that these rules are kind of standard. I mean, I did not read a single word from my sentence, and chart 0 is filled with these rules already. So this is constant. This is the same for all the sentences that you might have. This is not going to change. So maybe they can be preloaded to my chart 0. So chart 0 is fixed for any given sentence. It only depends on the grammar that you are working on. Okay, so what does this is predictor? Predictor, let's see what predictor says. Predictor says that, okay, if you are predicting something like that, a B, anything in your grammar that has a B on the left and some kind of an expression on the right, okay, you will put this in the same chart. Those predictor is coming, adding all those rules. Where do I call the predictor? Predictor is here, okay. An incomplete rule. So see, the rule is like dot s, okay. So this is incomplete, and that category is not a part of speech. This is not part of speech. So I call the predictor, and the predictor says that whoever has s on the left, VP, add this one. But then I have this one, whoever has VP on the left, add this one, right? So this is what I did with the predictor. Now what am I gonna do? Now I will read a word and I will move to chart 1. Okay, I read the word and it is book. Since I read the word it is book, and scanner came in. Remember who calls the scanner? Scanner is here. If I am in a incomplete state, okay, if the next category is part of speech, okay, for this one, verb, okay, it's a part of speech, then what am I gonna do? You write the scanner, okay, scanner. What does the scanner do? Scanner takes this, anything that is expecting a non-terminal, and if that non-terminal is a part of speech, then I am adding that word, okay, I am adding that word with B on the left to the chart. That's what I did. Okay, this one is added. Once I have added this one, I have a completer now. What does the completer do? This rule is done. Anybody is expecting a verb now can complete themselves. So I moved all of these verb dots from left to the right like that, because I have seen a verb now. That's the completer. Okay, then since I have these new positions for the dot, I am predicting this, and that. Okay, so I am predicting a noun phrase or prepositional phrase. That's what I am doing here. Okay, so this is chart 1. I already covered the first word, book. Okay, and these are the state, the rules, dotted rules with the states. Okay, chart 2 and 3. Again, read the word. Scanner read this word that. Now I have the determiner. With the determiner, there is a completer. With the completer, now I have the predictor. Okay, chart 2 is like that, and then I have chart 3. These are the chart 3 stuff. I read the flight. Again, just after the flight, my completed this nominal, this one, okay. And since I have this dot here, PP, there is a PP predictor. There should be a, okay. Since noun is a tag, okay, part of speech tag, I don't have a predictor for that. So this one is a VP, SVP. SVP is a completer now. SVP is a result from a completer now. And I found this SVP in my chart 4. This is 3. This is 2. Okay, so I am done. Book that flight. It looks like this sentence is not ambiguous. There is only a single S. Okay. And I didn't find any S's anywhere in the charts. So it looks like this is more, as you see, I could not find many things between 0 and 3. There is only a sentence. Okay, there is a noun phrase, book that flight. A verb phrase, verb phrase, another, no, this is not complete. Another verb phrase. Sorry. So this one is complete. This one is complete. Other than that, I cannot make any meanings because this one is not complete, or that one is not complete. So this is how the early parser works, top-down mechanism. As you see, it produces lots of unused trees that are not connected with the words. So we didn't save much, but it is again dynamic programming based, and it uses a table. Okay, efficiency for such a simple example, there seems lots of useless stuff. Why? Because it's the same problem. I have to check everything. Not all the paths lead to a solution, but I have to check them. Without checking them, I cannot know if they are good or not. Okay. Again, finding an S is not a sufficient thing. I need to add pointers to where I get this S, so that I can form my parse tree. Okay, back to ambiguity. Did you solve the ambiguity? Of course not. We were not expecting. If the sentence is ambiguous, then both of them will result multiple S structures at the last table entry. Okay. They both efficiently store subparts, so that's the nice news about it. But they will not eliminate lots of unnecessarily produced trees. Okay, without producing them, I cannot know if they are useless or useful. Okay, and ambiguity will not be solved by any of them. Okay, and with the human psychology, human language, we most of the time don't recognize that there is an ambiguity. Okay. We assume that when somebody says, one morning I shot an elephant in my pajamas. Okay, I assume that I was in my pajamas. I just woke up and I shot an elephant. Okay. Then after this sentence, how he got into my pajamas, I will never know. So that gives us the context. In these cases, it occurs us that I did not understand the first sentence correctly. So it was the second meaning. We go back and we check it. So most of the time we think that this is funny, so we laugh. So this is kind of a popular kind of joke. Okay, so in our culture, Karagöz Hacivat kind of does that. Okay, Hacivat says something to Karagöz, and Karagöz understands it in a misinterprets it. He understands it. He parses it in a different way, and for us that's funny, because what Karagöz assumes is not the intended meaning, and for some reason humans laugh at these kind of misunderstandings or misparsing. Okay, so human psychology is kind of different. We assign a default meaning to some sentences. If the default meaning doesn't occur, we kind of say, "Oh, what's going on?" And that's called ambiguity. And sometimes people, without realizing it, this happens. Okay, let me show you a few examples. I was going to show you these, but I didn't have any time. But let me show you. But this is going to happen after the midterm then. Yeah. Okay, how about this one? Can you tell me what? Just translate it to Turkish. This sentence. Scientists count whales from space.
Bilim adamları uzaydan balinaları sayıyor.
Bilim adamları uzaydan balina sayıyorlar. How about the other meaning? How about the other meaning? Can you see the other meaning?
Uzaydaki balinaları sayıyorlar.
Yeah, exactly like this. This is first one. Uzaydan balina saymak, and this is uzaylı balina saymak. Right? Usually we understand the correct intended what, but the first example is kind of different. San Jose cops kill man with knife. Well, I mean, maybe it is my not native language, but I understand the bad meaning. The cops kill the man using a knife. Well, intended meaning is, right? What is intended meaning? Intended meaning is the man was with a knife and they killed him, right? So sometimes with the newspaper headings, this kind of stuff happen a lot. Okay. Yeah, or for example, this one. What does it say? Doctor, no heart, cognitive issues with Trump. So the doctor examined Trump. He said that no heart, cognitive issues. To me, it says that this guy doesn't have a heart, and he has some cognitive issues. But the doctor says that no heart or cognitive issues. Right? So these are ambiguities, and we know how to live with these kind of ambiguities. Sometimes it is funny, but most of the time we know how to do it. Okay, that's it for today. I am out of time. And next week I am not going to do any lectures. We will start at 1:30 and we will do our online exam. Okay, see you next week.
Can I ask you a question about the exam?
About what?
Homework.
Yeah, sure.
The exam.
Exam, okay.
I think we are
Is my sound echoing?
Selman is also asking questions.
Somebody else is two people are talking. Okay, let me get the question from about the exam first. What is the question about the exam?
Isn't it short that you noticed that as just before 1 week because we are kind of busy, like we have projects and stuff. This is not a question, but I was just.
Well, I mean, the exam was supposed to be like last week or the week before that. We delayed it 2 weeks, and you were supposed to be ready, right? 3 weeks ago.
Yeah, but it wasn't that. It was kind of tentative, and we didn't even know if the exam was going to be a homework or.
So what are you saying?
We didn't know anything like we didn't know the syllabus was really tentative.
But
I think
tentative doesn't
announcing
mean
it-
that it's going to be 5 weeks off, right?
But I mean, if it was planned, I mean,
So what are you saying?
2
I
weeks
should
earlier.
I should delay the exam 1 more week?
Yes,
There will be more topics for you to study then.
it's okay for me.
How about other people? Let's vote. Who wants the exam next week or the other week? Next week. I am going to put next week here. Next week. Okay. Vote there next week. And the other week. Okay. Let me see your votes. Well, I cannot see anything. It is not changing.
We can see it's changing, and the not next week. The other week is 15 now.
Other
Next
week
week
15.
is
Next week is what?
2.
2. Okay, then we are gonna do it other week then. Next week I will cover more stuff. That's good. I can ask you more questions about dependency parsing. Yeah, very good.
That's okay. Thank you, sir.
Okay. So somebody is raising their hands. Who is that?
Can I ask a question?
Sure. Yes.
I sent you a few mails about first homework, second homework, and the paper assignment. I had disease, coronavirus.
Yeah.
and
I didn't I answer that. Just email me those. Okay.
I already emailed, but you didn't answer my.
No. You did
emails.
not email your homework. You just send an email.
All right. I will send you homework.
I thought I responded to you. Just email me your homeworks.
Okay.
Okay.
I had a question. I think I'm the last one.
Okay.
In homework, it says that you will use n-grams of Turkish letters, but I just realized this right now. I'm keeping n-grams as words. Is this correct? I mean, how should we keep our n-grams, as words or letters?
Whatever the homework says, of course, as letters.
Well, then
How are you gonna keep n-grams, 5 grams of words? That would be too big. Even with the letters, it's not that easy.
I was keeping the sequential 5 words, but I think it's not correct, right?
What?
I was keeping the sequential 5 words for 5 grams.
Yeah, but the space is too big. But I mean, there are 40,000 words in Turkish, and if you try to keep 5 grams, I mean, it's not going to be useful because your statistics will be very, very small, right? I did not say the word. It is not that difficult. Just convert it.
Okay.
I also thought it was words, and I just finished the homework, and it just takes too much space.
I don't. Yeah. I mean, we kept repeating the same thing. I mean, 5 grams of words. Even Google barely can do it with their resources. How are we gonna do it? I mean, we don't have the data. We don't have the space. But for the letters, it is not that difficult because if we eliminate those Turkish letters, there are 27 letters, and it is just 27 to the power 5. Again, most of them are going to be empty. We can manage it with the letters.
Is it okay if I send an homework with words? Because I thought you wrote it wrong or something. Because we were going to. You said we are going to produce sentences. I thought that for us to produce sentences, we need words as.
Well, you're gonna
there.
produce sentences, but you're gonna produce them with the letters, not the words. If you put the letters
thought-
together, they will make
I
up
thought
some.
it was a full sentence. Sorry.
Now it makes sense because the data set, the sentences weren't too meaningful. Right.
Yeah, okay. So that homework is not supposed to be a hard homework.
Can we get at least 1 day extension?
Okay, 1 day extension then.
Right, thank you.
Okay, I'll see you next week for a new class, new lecture.
Sir, can I ask a last question?
Sure.
How many extra days for homeworks I have?
Oh, okay, because you have the medical report. I mean,
Yeah.
after your medical report, let's give you like 2 weeks. Because
Alright, thanks.
other people got 2 weeks and you are gonna get your 2 weeks.
Thanks.
Okay. Okay, good. See you tomorrow. See you next week.
İyi günler hocam.
Sizlere de.